Okay, good afternoon and welcome to the 7th session of the Sunoikisis Digital Classics Spring 2018 semester. This session is the second of two sessions on tree banking. Last week, Mario and Polly showed us how to tree bank and a few tools around that. And this week, Haug from Oslo and Francesco Mambrini from the DAI in Berlin are going to show us what one can then do with tree banked material once they've been tree banked in the first instance, and with a focus again on Greek and Latin. So I will hand over. I think Dag is going to start off. I'll hand over to Dag to get us going.
Okay, so hi everyone. I'm Dag Haug from the University of Oslo. Speaking now from Gothenburg, where I'm visiting, but should be fine. So I'll show you share my screen so you can see my slides. Here we go. Now you see my slides, right?
Yep, correct.
So I'm going to first introduce you a little bit to regular expressions because they're very useful for querying tree banks. But they're also useful for lots of other things. So I believe that they will be covered in later courses as well during this Sunoikisis syllabus, but I think it's a good thing to repeat anyway. So that's what we're going to start with. And then afterwards, I'm going to tell you how to query syntactic tree banks with the INES infrastructure, which is where you'll find the ProEL corpora, the ones we've developed in Oslo. But hopefully, I think many of the techniques I'm going to illustrate for querying corpora in INES are also going to be useful in other applications because there are lots of similarities between various tools you can use to query tree banks. So let's start with regular expressions. So what is a regular expression? Well, basically a regular expression is a pattern that will match a certain set of strings. So it is a string itself, but it matches more than just itself. So one single regular expression can match many different strings, and that's what makes them powerful and useful tools for querying things. And these regular expressions are used in a number of applications. So, for example, in corpus query engines, which is what we're going to look at today. But there are also text editors that can do regular expression searches and regular expression-based replacements, which actually allows you to manipulate text files in powerful ways. So they're very useful. So let's first talk about how we build regular expressions. Well, the basic building block is pretty easy. It's what we call literals. So basically characters matching themselves, as it were, right? So the regular expression A will match the first occurrence of A in a string. So nothing surprising there. It's quite easy. And this pattern works for most characters. There are a few special ones that have special semantics when they're used in regular expressions. And these you can't match directly. So that's the backslash, the caret, the $sign, the dot, the pipe, the vertical line, the question mark, the asterisk, and the plus, and parentheses of all types, normal, curly, square, parentheses. Now, if you want to match those, you need to escape them, as we say, by putting a backslash in front of them. So I'm going to show you this later on. So as I tell you here, there are lots of online apps that will let you practice regexes, and that's actually a very useful tool just to see how they work. So we can look at one which is called regex tester. So this gives you a little window where you can put your test string, and the window is indeed very little, so I'm just going to take a little bit of text, and you'll see here. Oops, I put this as the regular expression. That's not what I should do, but this is the test string, right? So if we put in an A here now, you can see that we match all the A's. By the way, I see this thing does not work perfectly in Firefox. So maybe, sorry, in Chrome, which will, so I should switch to this, sorry. I'm going to remove this. And I will now instead, it's a bit annoying, but screen share my Firefox. So here we can see the whole string. So if I, type an A, I match A's in the text. So that's not surprising. That's what you would expect. And then also finding S's are easy. I mean, this all works in the way you would expect. Now, if you wanted to find the square brackets, we cannot do this. Right? We cannot just simply search for a square bracket because that has a special semantics that I'm going to tell you about later. So we need to put a backslash in front of it, and now we match exactly the things we want to find. The same thing for the comma, for the full stop. You'll see a full stop is actually a wildcard in regular expressions. So now we match every single character in the text. If you want to match literal full stops, we have to put a backslash in front of it. Now we find it. We can also sequence things, right? So we want to find all the occurrences of ST. That's easy. And we can also find, let's say, we want to find all the stops that end the paragraph for some reasons. Let's say we want to split the text into paragraphs. We could just find this, followed by some white space, followed by a bracket, right? So now we find the relevant points in the text, which can be useful if you want to manipulate the text and divide it into paragraphs or whatever. So far, there's nothing very special. Regular expressions are just normal queries with this wildcard dot, but there are different things you can do. For example, you can define character classes. Let's say we want to find either A's or E's. And I'm going to do this. Now I match some A's and some E's. Partes, right? We have a match here in the A, and we have a match here at the A. We can also do negated searches.
Could you maybe zoom in a little bit, Doug, so we can see a little bit more clearly now?
Oh, I need to increase the size?
A little bit would be great, yeah. Thank you.
Yes?
Perfect, great.
So now I put in this little caret. That's a negation sign. So now, if I do, for example, this, I match everything which is not a vowel, right? So inside these square brackets, I can do this to match all vowels, and I can negate it. And now I match all non-vowels. So that's useful for many cases. And then we can also do ranges. So let's say we want to do anything that is between A and Z, a small letter, right? So not a capital letter. We can do all the capital letters, and we can find, only, this is less useful, but only characters early in the alphabet, right? A, B, C, D, E. This will match that. So that's, yeah, possible. There are also other kinds of predefined classes, which may depend on the actual regular expression engine you're using. For example, this \W will in many engines match any word character. So an alphanumerical character, a letter, or a digit. There's this \S matching white space, and various other things. So to know more about that, you often have to read up on the particular regular expression engine you're using. Okay, so if we wanted to find words, for example, words ending in S or is, let's say you're interested in the accusative plural, which can end in S or is, you may want to extract all words ending in S or is. That's going to give you some false positives, but also the material you want to work with. So in that case, we combine what we already learned. So I'm going to find something that is an E or an I, followed by an S. But you see, we still match things inside words, like fortissimi. So to make sure we're at the end of the word, we make sure there's a space following, right? So now we find omnes and all words ending in es, not just accusative plurals, obviously, but actually here all the es words are dative or ablatives. We can also find the paragraph references. So on a small text like this, that would not be too useful, but in a bigger text, you may want to extract them. So we know that we can see from the structure of the text that a paragraph reference is something enclosed in square brackets. So I'm gonna give you, we need an opening square bracket, and then, no, this is gonna look a little bit forbidding already. We need something that is not a closing bracket. So as many as we want of those, that's the star, I'm getting back to that, and then we need a closing bracket. Now you see we have an something that matches 0 or more of the preceding token, which is anything except a closing bracket. And then we match the closing bracket at the end. So this gives us all the paragraph references. And in general, if you have knowledge about the structure of the text, of the markup of the text, etc., you can use this knowledge to define the correct regular expressions to extract exactly the knowledge you want. So that's very useful. Another thing you might want to do is to match line ends and beginnings. So that's the caret again. Now, the caret also serves as negation, but the caret is negation when it's inside the square brackets, and when it's outside of square brackets, it matches line starts. So if I do this, you can see well, that does not match. So there may be a difference in this particular engine. Oh, sorry about that. But the caret marks the beginning, at least, right? Matches the beginning of the string, or the beginning of a line, if a multi-line flag is enabled. So that can be useful. There's more power to the irregular expressions. So, for example, we already saw this for disjunction, basically, AOE, but you can also do disjunction of bigger fragments, of sequences. This will find every instance of string, EA or AE. So now we have EA and provincia, right? So both of those are matched. And with this, for example, we can now start doing more linguistically interesting queries. For example, we can try and find all forms that potentially belong to the second declension. So how would we do that? Well, first of all, we know there are some forms ending in E and O, right? So that's genitive and then dative ablative, singular. But we also have forms ending in is and os. So now we do this. S question mark, that means maybe with an S. So now we're matching E, O, is, os. And then we do a disjunction because we also want to match, and right? So now we find all the forms, and to make sure we have the right scope for the disjunction, we should do this. And now we find all the forms that potentially belong to the second declension, except as it stands, we may find word internal things like in the visa. So we want to make sure there's a space following, right? So in this way, you can extract morphological patterns that you're interested in. Of course, as long as there's no annotation in the text, you're only going to find pure character strings, right? We find is, no matter whether that's omnis or belgis, right? So whether it's a nominative singular or a dative plural, the regular expression obviously does not know anything about. For that, we need more structure annotation, and that's what we have in Treebanks. So that's what we're getting to. We've seen most of what we need to build regular expressions. We've seen the so-called quantifiers, question mark, 0 or 1, star, any amount of S's, 0 or more, and plus at least 1, right? So this will now match is, and so on, right, with multiple occurrences of S. And basically, by putting together the building blocks you've now seen, we can do a lot of powerful searches. There are some exercises you can try in the slides on slide 11 and 12, but we're going to skip those now in the interest of time, and we're going to apply our knowledge of regular expressions rather to search Treebanks. So I'm going to leave this page, and I'm going to go back here and make sure I rather screen share this one, the Chrome window, and then here, yeah, good. So let me find my slides. So you can have a look for your reference. These slides will be put on the wiki page, and then you can look up everything you need here, and you can do the exercises. You can also see there's also some examples here of more advanced usage where you can do powerful find and replace commands with an XML file in your text editor if you want to transform it for some reason. So that's quite interesting use. Sometimes you want to extract data that you can use in your research from a file that doesn't have it. And to do that, you need to use captures, but I'm going to leave that for now. So, Treebanks, that's what the rest of the talk will be about. So a treebank is a representation of the syntactic or semantic structure of sentences. So there can be syntactic, normally you find syntactic information in a treebank, but there are treebanks that give you more semantic structures as well. Those syntactic structures can be represented through constituencies, so phrases, words that belong together, or dependencies, words that functionally go together, right? So constituencies are words that actually stand together. Dependencies are about words that belong together. And since you've all studied Greek and Latin, you know that those do not always go together very well in Greek or Latin, much less so than in English, for example. So for that reason, it's generally agreed that dependencies are the best for free word order languages, because you want to know what goes together in a grammatical sense and not necessarily what is next to each other, because that's doesn't always mean much in a language like Latin. So probably the most important motivation for doing syntactic annotation of a language like Greek or Latin is to be able to query these structures. So Treebanks have many other applications in other, especially for modern languages, right? You can train parsers, you can make the computer understand language and so on. But for Greek and Latin Treebanks, the motivation is really, most of the time, to be able to study the linguistic structure that is encoded in them. Now, unfortunately, the structures in the Treebank are complex. So the query languages are also complex. That reflects the structure. So if you did try to do some Treebanking on your own after the previous talk, you will know that was pretty complex. But if you learned that, then querying the structures is going to be easier. So the treebank I'm talking about today is the Proel treebank, which is slightly different in it's developed from the ancient Greek dependency treebank, but you'll hear about that afterwards. Proel is a treebank that covers ancient Indo-European languages, so most of it is Greek and Latin, but we do have other texts. We have a parallel corpus of the New Testament translated into ancient Indo-European languages. That means we have the Greek original, but we also have the Vulgate, we have the Gothic translation, we have the Old Church Slavonic, and we have the Classical Armenian translation. So that's sort of the core of our corpus. And then we've done pilot annotations of Vedic, Hittite, Middle Irish, and Lithuanian. And the eventual goal of all this is to have a parallel treebank of all ancient Indo-European languages to provide support for comparative Indo-European syntax. But today we're only going to focus on Greek and Latin. And that's also my main motivation for doing this work. So that's why we have done a number of Greek and Latin texts beyond the New Testament. So here's what we have. We have Herodotus. About half of the text of Herodotus has been treebanked. We have Srances, so that's a 15th century text that's probably unfamiliar to most of you. That's an eyewitness description of the fall of Constantinople, a fascinating text. You can have a look. We have about half of Caesar's Gallic War. We have lots of letters to Atticus by Cicero. We have some parts of the Ophiuchus by Cicero, and we have a whole Peregrinacio Aeteria. So we're also trying to get some diachronic depth in this corpora. So I think that will be very interesting. And there is also Petronius coming up. That's almost complete by now. So that will be added in the next few months to the corpus if you want to study Petronius. So the annotations we add are pretty similar to the ancient Greek dependency tree bank. In the morphology in particular, syntax is different in details, but otherwise quite similar. And then we have also something which is unique to our tree bank, which is information structure annotation. That is, we encode the NPs in the text, the noun phrases in the text, for whether they introduce new reference or talk about things that have already been mentioned. So I'm not going to talk more about that today. That's there in the tree bank. You can query them, but it's a bit more difficult, so I'm not going to talk about that. And the same goes for semantics. We have some semantic information. For example, you can find out whether a noun phrase refers to an animate object or a concrete object or an abstract object. That kind of categorization is also available. Now, our data are available in lots of different formats. Three basic ones is the phony application, which is you can use to browse the text, and you can do simple single token queryable annotations. Actually, I should also show you. I'll put this on the slides. I forgot to mention, but we also have the Syntacticus website, which kind of does the same things these days, where you can browse the text. So I'll show you a little bit. That's actually quite interesting. So, for example, if you're working on the Vulgate, you can get the Vulgate in parallel with the Latin and the Greek. And you can click on some, let's find a slightly more interesting sentence. You can click on this one. You get the annotation, right? The parts of speech. You get the morphology. You can get the syntax of the sentence, so the syntactic tree. And then you can get the Greek and Latin in parallel. So that's pretty nice. So here, you see the Greek and Latin text lined up, and you have the trees on both sides. So you can use this to study comparatively, translation techniques in the Vulgate, right? To see how things fit together. The basic picture you get is that things are very similar, right? So you have lots of mappings like these, one-to-one mappings in the same word order. Sometimes there's a displaced word. And of course, in those cases, you need to go back to the critical editions and check. And many times you'll find that, oh, there is a Greek version that has the variant that Jerome was actually translating. So he actually does this word by word in many cases. But sometimes you find interesting stuff here as well. So that's a nice parallel view. It is possible to query the parallel text as well. But I'm not going to talk about that today because that's pretty complicated. You need to build two syntactic trees and match the nodes, so that's quite complicated. Let's see. So to my slides. That's for me, and then Syntacticus, our new application. So we're moving everything to Syntacticus eventually. I'll put in a link for that in the slides before I put them online. Then we have the Ines webpage, which will allow deep querying of morphology and syntax online, so in a browser. So it's useful. You don't have to install anything. You don't need to know any programming. You just need to learn the query language, which I'm going to teach you today. And it gives you fairly deep querying of morphology and syntax. But eventually, if you're working with Treebanks and that becomes an important part of your research, you really should look at the source files, right? So those are available on GitHub. You can download them and you can manipulate them. You would like to learn some basic programming, XML programming, and that's where you can do the really deep things. But that requires more knowledge. Probably an entire course could be devoted to programming for that. But for the kind of fine examples that are relevant for my research, then Ines is the tool you want to go to. That's what I'm going to talk about today. So I'm going to skip these pages here. Basics of Ines. So Ines is a portal offering access to many Treebanks of different languages. Works best in Chrome. That's why I'm using Chrome now. And to use it, you need to know at least two things, right? So you need to know the specific query language that is defined by INS, which is similar to something like Tiger Search that you can use for querying other tree banks. But you also need to know something about the way the corpus you're looking at is built up, right? So the way we have annotated stuff in Proel. Unfortunately, this is similar to what they do in HGDT and what you heard about last week, but there are some subtle differences too. Now, if you go to the INS web page, I'm going to go back to the first page. You're presented with this. Welcome to INS. And the first thing you need to do is to query a tree bank, to find a tree bank, select a tree bank. So I go here, tree bank selection. Then you see there are all sorts of languages represented. I'm going to use the Latin today. There's also ancient Greek, and there's modern Greek, and there's our classical Armenian, etc., etc. And lots of other languages. There's also Old French, Old English. I mean, both historical and modern languages. Then you get lots of different Latin corpora. The Proel corpora are the four uppermost one, right? So the Caesar, Gallic War, Cicero, Letters Staticus, Latin New Testament, so the Vulgate, and the Peregrinatio Aeteriae. These are offered in various versions called universal dependencies. I'm not going to talk to you much more about that. The universal dependencies corpora contain the same information, but they're in a different format, which is a standard format for tree banks across languages, and also across Latin tree banks, right? So in the universal dependencies format, you'll find not just our Proel corpora here, you'll find the Index Thomisticus tree bank, and you'll find the Latin dependency tree bank. And they're all annotated in the same way there, at least in principle. So Giuseppe and I and Marco have made an effort to converge when we convert our original annotations into UD so that they become as similar as possible. So basically, if you want to combine data from the ancient Greek dependency tree bank and the Latin dependency tree bank and even the Index Thomisticus with our data in Proel, you can do that via INS. So you can query the original AGDT dependencies, but you can query the conversion into universal dependencies. So that's quite good. And then you can combine our data. But for today, I'm just going to use the Proel version. So I'm going to unselect everything and then select these. So now we have these, and then we can go to one of them. And you get some metadata, and you have to accept the license. So let me see. Yeah. So you get a list available. Yeah, documentation will take you to the documentation of the query language. Yes, I should show you this. If you go here, you can see documentation of the INS search walkthrough, and all sorts of other documentation. The query language is really what is most interesting here. I believe even if you go, no, it's probably here. Links, go to links. There is a video of Doug demonstrating Proel tree banks in INS. This is actually the Sunoikisis course from last year or the year before, I think. So there's a link to that from this webpage. Anyway, we're going to look at the tree banks. So we see the familiar beginning of Caesar's Gallic War. And you can click on a sentence and you get the syntactic tree of that sentence. Right? So this is basically just browsing, as it were, right, without querying. But that's useful. Often you need to, in order to be able to query for a specific construction, you need to find an example of it, see how it's annotated, and then use that knowledge to be able to produce a correct query. You can, if you click on it, you're going to get the tags that word has. So you see gallos as lemma galli as part of speech, NB. You need to look that up in a table that I'll show you later. That basically means a common noun, and it has certain morphological features. Plural, masculine, accusative, inflecting. Again, you need to look those up in a table. So the data you get are basically words, also known as nodes in the graph world, and you have links between them, also edges, called edges, right? And the nodes have these attributes called lemma, pos. So the ones you see here, lemma, pos, and morph, and they also have an attribute called word, which is the form of the word in context. So basically what you see in bold here. So every node has certain attributes, and then you have these edges, and they come in two types, and they have labels, primary and secondary edges. We're going to focus on primary edges today. You can see we have a secondary edge here, which tells us that gallows is the object of two different things, but let's not care about that today. We have the subject edge, we have the oblique edge down here, and another subject edge as well. So the edges have labels, or the arcs, or whatever you want to call them, have labels. Now, if you want to query the attributes, you do it basically like this inside square brackets. So word equals sum, we'll find all instances of sum in the tree bank. That may be none actually. I'm not sure. I mean, it's not the most frequent. So let's do this, because now we're only looking at Caesar, right? So but if we do est, we find lots of words, right? Now, of course, querying the word form by itself is not very interesting, because that's the kind of thing you could do without a tree bank. So you want to do something with more structure. So one thing to notice at once is that what comes after the attribute is actually a regular expression. So that means you could find est, and this would be is and est, but in this case there's probably not many cases of est. So let's do but that's it's not a verb. Not much found in Caesar. Yeah. But let's just leave querying the word form, because that's going to be very similar to what I just showed you about regular expressions. So what we want to do to exploit the full power of a tree bank is to query these attributes, right? So, for example, the part of speech. So, part of speech is a string with two characters. The first character gives you the major part of speech, which may be pronoun, for example, and then the second character gives you a subtype, interrogative, relative, or whatever. So you can look those up. Here, you see that, for example, D, capital D is an adverb, and then DF is an ordinary adverb, DQ is a relative adverb, like ubi, and DU is an interrogative adverb, like ubi when used as an interrogative. So if you want to find all, let's first do the easy thing. We want to find all interrogative adverbs. 24 of them. We can change the overview. So we find them here. So kur, interrogative adverb, and here you go. You find the syntactic structure. Now, if you want to have the relative adverbs, that's DQ. This 113, so more, not surprisingly. And then if you want to have both of them, that's where the power of regular expressions come in, and you want to do this, right? A D followed by either a Q or a U, and then you get both kinds of examples. So this is where regular expressions become very useful. Similar things for nouns, right? NE finds all proper nouns, NB finds all common nouns, and NBE finds all proper and common nouns. And conceptually, it's different, but you could also search for N dot, would find all types of nouns. But in this case, there are only proper and common nouns. So there's not much more you can do. Let's just play with those. So let's see how many nouns we get, 1,420. And then this should give us the same. Yeah, and that's what we get. Good. Now, if we look at these sentences, the part of speech tag is relatively coarse grain, right? Only 2 fields. But then we have the morph tag, which is much more complicated, right? You have lots of different, so especially for verbs, right? So divisa, this encodes that this is singular, perfect. Let's see if I can do this online. I probably have to look it up. It's list feminine, nominative. So this gives us very complicated strings. There are 10 fields. First is person, number, and then number, tense, mood, voice, gender, case, degree, strength, and inflection. So this gives us very complex strings. That's how the morphological structure is encoded. And by the way, this is, I believe, similar, if not identical, to the codes you find in the ancient Greek dependency Treebank. So here we can look up the first letter, right? So for example, if it's a third person singular pluperfect, you get 3SL, and then maybe it's an indicative, I, P passive, etc. So these are very complicated strings, and most of the time we're only interested in a single field. So that's why regular expressions become crucial to do what we want. So here's an example of a full string, and then I can obviously query this. There's no example of third person singular perfect indicative active inflecting. That must be wrong.
You need to change it to morph.
Oh yes, right. Thanks. Yes, very good. Yeah, it'd be surprising that there were no third person singular indicative perfects. So here, yes. Now we get the relevant examples. So in this case, fuit. Good. And we can go to the next match and so on. But most of the time, we're not interested in all this stuff, right? We might only be interested in third person singular verbs, or only perfects, or we don't want to be specific about all the fields, right? So that's when regular expressions become important. No, before that, I can show you a few other things. So here, singular, and then ... We don't care because those are verbal rather than nominal fields. And then we have a Q in the gender slot. So that's here, M, F, or N. So we can look for that. We find the examples we want. I'm gonna. So here, for example, ulteriore is an ablative of the kind that could be both masculine, feminine, and neuter. So, yeah, the next slide is about regular expressions about open morph, because as I said, we're typically not interested in all the fields, right? Let's say we only want to find perfect tense verbs. Here's what we do. Morph ... r ... star. If we go back to the fields, dot matches everything, right? So we say person, I don't care, number, I don't care, r gives you perfect tense, and then dot star means whatever for the rest of the fields, right? So this will give us all perfect tense verbs. (153). And we can find superlatives in the same way, and we can combine several attributes. So here, for example, if we're interested in the distribution of ablative endings, right? So you know the ablative or third declension adjective can end in E or E. We can now look that up. So this says ignore all the fields until I get to the case field. That should be ablative. Then ignore the rest. Part of speech should be adjective, and the word should actually end in E or E. Read the examples, and now we can sit down with those and do research on this. So ulteriore again, and whatever, presente, etc. So that's useful if you want to research, for example, how those endings are used. Now we can also name those nodes, and this becomes important not when we do morphology, but when we do syntax, because you have several nodes we're manipulating at the same time. So the query, here's the query I gave you. I can prefix that with a hashtag X, which names that node as X. And then we can combine several constraints. Now, you see, we could already combine several strings. So an equivalent query would be this, where we say X should have morph so, and X should have polyspeech A, and X should be a word form ending in E or A. Those two are equivalent. But once we have syntax coming into the picture and we're querying several nodes at the time and relations between nodes, the node names become important. But an interesting thing about node names is that they can be used to query tables. So for example, if I take this query and I put it in here and I run it, I actually need to go to the query view. I can get a table like this. So the different morphs, polyspeech, and the different words that I find that match this. So that can be useful. And you can download these tables, right? And you can also click on them and you can get the actual examples. So you can go to that. So that's useful also for doing this kind of research. Now, the table is only created when you use node names. So that's so this is written about in the INS documentation, but it's useful to know. So now, finally, we will try to query syntax, and then everything becomes a bit more complicated because now we're not dealing with just simple nodes and their attributes, but with a two-dimensional structure over those nodes, right? The syntax is a tree, as you saw last time when you did tree banking. So there are two dimensions, right? There's the vertical dimension, which is dominance or government. So basically a verb governs its arguments. Preposition governs its complement, etc. That vertical dimension is represented with the operator less than. And the horizontal dimension, which is the left to right dimension of the tree, the word order, the precedence, is represented with the operator dot. So you can see examples here. X dominates Y and X precedes Y. And you can use a star here too, which has a similar semantics to what it does in regular expressions to generalize these operators so that it's not direct domination, right? So this expression here, X dominates star Y, means that X is somewhere higher than Y in the tree. There's a Y under the X in the tree. Not directly under, not necessarily directly under, but somewhere under it. Similarly, the dot means directly precedes, whereas dot star means precedes by any number of intervening tokens. Now, in most of the time, we're not just interested in the dominance relations, but also the labels on those, right? So, and those can become quite complicated, so you can read up in the documentation on the Broya corpus if you want to do that. But for now, we're just following familiar labels from traditional grammar. So that's subject, object, adverbial, attribute, and complement clause. Those are the ones we're interested in. And then we add those directly after the dominance operator. So this, let's first take this part. This just says, give me some node X that dominates a node C with a comp relation. So that's, let's rather look at some examples rather than the table. Basically, C is the complement, is a complement clause under X. So here's one example, an ACI structure. C, X dominates C. So you see another nice effect by the way of using these variables. You can find where in the tree you matched. So that's actually very useful. So this gives us any complement clause. And then I think the example I wanted to look at here is now instances of nunc inside a complement clause, just because that's potentially interesting when nunc is used in indirect speech. Does that refer to the speakers now or the narrators now? That's a kind of research question you might have. So how indirect is the speech? we can do this, right? And now I'm reusing that variable, right? That node name. So give me any C that is comp dominated by X and that itself dominates the word nunc. I think those are the wrong. There are three cases, right? Nunc esse in Gallia ad centum et begint Emilium numerum. You can look those up, and here's a longer sentence where the nunc is pretty deeply embedded. Where is it? I don't even see it. Wow. I'll have to tell our programmer. There's no nunc in here. Yeah, I don't know what happened actually. Oh, there is the nunc. I just can't find it. Oh, because it didn't give it a variable name. Is it over here? Oh, here. Sorry. Yeah, skipped it. Here's the nunc. So you see that because we use the star operator, we find nunc at any level of embedding under this C, right? So we know from this first part of the query that we're inside a complement clause, and then inside that one we look for the whole subtree, which can be pretty complicated, as in this case. You know, if you read any Caesar, you know that in direct speech constructions can be pretty complicated. So that will give us that, and I think I'll do the next slide as well, and then I'll leave the rest because Francesco needs to get some time. So let's find all subjects. This is very similar, of course, but it will show you some, that you really need to understand the query, the structures we created before you do the queries, because this is a vanilla case of a subject. Everyone would expect Gallia to be the subject. But if you do this in query mode, you'll see that the most frequent case is probably, oh, it's not sorted by frequency here, but I can maybe do that. Yeah, you get verbs as subjects, and you may wonder what on earth goes on there. Well, what goes on is that the verb is the head of a relative clause. So that's what's going on. Yeah, let's go to see. I am kind of running out of time, so I think I should stop here. There's the last few slides are about replicating a study of word order without corpora. I think there's enough information in there that you could try and follow that by yourself and implement all the different steps. Build your query step by step, and then get this monster regular query expression that will find you everything you need. So I think there should be enough information in the slides, and you can also contact your local teachers and they can get in touch with me if there's anything that needs to be explained. So I think I'm gonna stop here and leave the rest of the time to Francesco.
Thank you very much, Doug. Thank you very much to Gabby and Monica to inviting me to present here. I will just start the share screen. Can you all hear me? Is everything fine?
Yep, you sound great.
Perfect. So let me share the entire screen to you. And right now, hopefully you should be looking at my slides, right?
Yep. Yep.
Perfect. So let's jump to the topic. So Doug presented, and I have to say he did a fantastic job, what querying a tree bank means, and he gave you all the information about querying a syntactic annotation and the use of different layers of linguistic information that is encoded in such a beautiful object, complex object like a tree bank. My part would be to tell you what to do with the other great project that it's around there that Doug mentioned a couple of times for the ancient languages, as a tree bank of ancient languages, both Greek and Latin. Though I have to say that my interest lies more on Greek, and so probably you will hear that most of the examples I do are on Greek. we can discuss about how to port everything that I will tell you to Latin. And I am referring to the ancient Greek and Latin dependency tree bank, or if you want to, it's generally abbreviated to AGDT if you refer just to the Greek part, so ancient Greek dependency tree bank, or AGLDT, ancient Greek and Latin dependency tree bank. So before we say anything about querying, or we take over the same kind of exercises that Doug was proposing to you, let me start by saying something about this tree bank, this ancient Greek and Latin dependency tree bank. It's a project that was started and maintained by the Perseus project. You're probably familiar, all of you, with the Perseus Digital Library. The Perseus Digital Library in 2007 and then 2009 started the parallel production of these two tree bank of, which are more oriented towards classical text of the classical and archaic period of the Greek and Latin literature, in comparison to Proyel, which started and focused, as Doug said, on the New Testament translations, but still incorporating other diachronic texts. The AGLDT focused more on the typical classical literature. So, for example, in 2009, we started with Homer and Aeschylus for the Greek side. The Latin side has a little less, but it focuses more, yes, on text, but pretty much the same text, I have to say, that that Proyel has, though in not in the same, not at the same size as Proyel. So a little bit of the Vulgate, a little bit of Cicero, a little bit of Petronius, and so on. The Greek, though, has been maintained and updated at a higher pace and with more enthusiasm, I have to say. So it now reached a quite substantial status of 750,000 annotated words, pretty much, last time that I counted it. It includes a lot of poetry, so this is a difference from Proyel, another difference from Proyel. For example, it has the whole text of the two Homeric poems, Iliad and Odyssey, the whole complete and extant poems of Hesiod, so with the exclusions of the fragments, but it has the pseudo-Hesiodic Shields of Heracles, the Theogony, and the Works and Days, and a substantial representation of tragedy. The whole set of the 7 complete tragedies attributed to Aeschylus, and 5, so almost complete, of Sophocles, no Euripides, though, plus other texts. I will show you maybe an overview of them. And then there are a few prose texts, Book 1 of Herodotus, like in Proyel, Book 1 in Thucydides, and a few orations. So let me just show you the home page of the project. So this is the home page of the project. The links will be in the slides, but if you Google Ancient Greek and Latin Dependency Tree Bank, you will find it very easily. And here's the complete list of the texts. So you will see that this is the Latin Dependency Tree Bank, and it says that doesn't have much completed texts. And there are also few informations like the annotators and the copyright and the status and everything, and a link to the actual files where you can go and download the files as they are. If you click over there, you will be taken to well, let's do it, to an instance of the Perseids and developed tool Arethusa, which is a beautiful tool for browsing and annotating tools. So you will be able to just go look around on and inspect those trees, but not edit them in any way, that you could actually save them or something like that. So let me close this and go back to my slides. So here's a little view of what kind of information there is in the ancient Greek and Latin dependency tree bank, so how it is encoded. And this is the format in which those tree banks are distributed. So it's an XML file, basically, where you can see that all the sentences are separated as elements, and each word has a few attributes that encode exactly the kind of information that Doug was talking about. So the word order, you see it's in this ID, sequential ID of the words that corresponds to the sequence in a sentence. And then some morphological information like the lemma, the form itself, of course, the lemma, and as Doug said, a post tag, a tag that is encoded as a series of 9 letters, 9 positional arguments, and for each of the position has a meaning. So the first one is the part of speech, the second one is the person. So you see that, for example, for word number 6, which is a verb, you also learn that it's a third person. And then obviously you'll have to look up all those, the meaning of these different alphanumeric characters in a table, pretty much like the one that Doug showed. But that will not be the focus of my presentation. And then you have some information encoding the dependency relations. So, for example, you will learn that word number 1 has an head, so depends on word number 6 by simply looking at this XML file. Word number 6 is indeed a verb, and that the relation would be, it's kind of cut, but you can still read it, as BJ, which if you read the guideline would know, as you can imagine, that it corresponds to the subject. So you see that this word is actually the subject, is connected with a syntactic arc to word number 6, and it's the subject. And this information encodes the fact that this word is the subject of the verb in position number 6. So this is a very, very quick overview on the ancient Greek dependency treatment. But the most important things that you can remember, ancient Greek and Latin, most important things that you should remember are that some important classical texts like Homer or the tragedies are completed there, so are there with full annotation at those levels, with those information that I showed in the slide before. And then there are a few other excerpts like orations of Lysias, again, if you're interested in Greek, and all the texts that were there. So what can you do with that, since we are here to talk about this? This is the subject of our presentation today. What can we do with those texts? Well, the short answer to that is that we have no software that works natively with the AGDT format, and where you can go online, like you can go to Ines and query all those 700 and counting 1,000 words of annotated Greek or the Latin counterpart, or anything that, or any software that you can download and can work natively with the AGDT format that I showed in the slide before. What we do have, sorry, is a few third-party tools that are also mentioned on the website, and in particular one that I will present briefly in a few minutes, the structural search developed by Nick Callan. The other option, that it's basically what the professional people, yes, that work with the ancient Greek dependency Treebank have been doing so far, hack it yourself. What does it mean? You can download, as I said, those files, and then you can start querying them using languages or programming or coding programming languages that can retrieve the information by reading it from the XML files. I will not talk about that. You can refer to Giuseppe Celano's tutorial, a presentation that he did in last year's Sunoikisis, which will be linked in the slides, as you can hear, using a particular query syntax for XML, which is xquery. Another option is, that's one that I use, and I will talk about it briefly, or at least show how to do that, is loading everything into a database, converting anything into a structure that can be read by any database management system, and then you can use the query language for this database that is natively provided by this database management system. But that's probably disappointing for many of you, because it's you would think that it's too daunting. I mean, anything like that, it's simply too bad. But at the same time, if you want to just pause for a second, and it gives us the one good opportunity, I think, which is to think about one aspect. What do we want from a query language, from a Treebank? And this is important because this is exactly reasoning about the requirements that we have when we approach this problem, how to query Treebank. I think it's a powerful exercise because it's gives us an opportunity to test, to assess how good the tools that we have are, and B, if not directly implement our preferred solution ourselves, to just get in contact with the people that are working and let them know what your expectations are in terms of requirements. I will tell you mine, and then if we have some time for discussion, we can continue that in other occasions. You can tell me yours. So mine would be that what we need is a system and a language to work with that it's intuitive, which means easy to learn. So, for example, it might be easier to just write part of speech equal verb than to do regular expression on the first position of a 9-letter string like the one that we encode in the XML. But that's not said that the other one is a bad solution. It's what we have in many. It's what work out of the box. We need it to be powerful. What do we mean by powerful? I mean that it must be able to support all the stuff that Doug has showed that Ines can do. So support regular expression because they are incredibly helpful. Support research on orders, like, okay, I want constituent, like subjects that come before the verb, only before the verb. And it must be able to work with complex dependency chains. We all know that we can construct, the language is working like that. We can construct complicated sentences ad libitum. So I can say that I want a verb governing a noun, governing an adjective, governing a preposition, governing another noun, and so on and so forth. And a query language must be able to deal with all this complexity and to extend it in this in that. And so I think that a very good query language and a very good software that implements query language for Treebanks is the one that have no problem, in which we have no problem translating our research questions into a formal language. So it's very easy to map, right, your research questions that you express in natural language to the formal language. That's easy it's easier said than done, obviously. And then I had my own second level requirements that in my experience are extremely important. First of all, like Ines before, you haven't noticed that, but it's very fast, and that's good. And that's not something that we must forget, because Treebanks can hopefully will, if we want them to be comprehensive and useful to do corpus-based research, must scale up to the level of hundreds and thousands and probably even millions of words. Still, we must be able to query them in a reasonable amount of time. And here's my view. I think a very good query language must support a production of at least a couple of outputs, pretty much like Ines did. As visualized trees. Good thing about Treebank is that they are very helpful to visualize what we want, the structure of a sentence. And or support another view of the results as tabulars and in tabulated form, tabular form, and or statistics. So, for example, if I just want to count the structures that Doug was querying before, I can just have a number that tell me, okay, those are the matching levels, or I can generate quickly tables like saying, okay, this is the number of objects preceding the verbs is 100, the number of objects following the verb is 50, something like that. So I must be able to get this output out of my query. That's ideal. Here's a point that is sometimes underestimated, but I think it's very important. They must synergize well with the digital editions of the texts. Sometimes you get information in digital editions that you don't have in Treebanks. And we'll see an example in a second. And I want them to be extensible. Doug's mentioned the fact that you have in Proya, for example, animacy annotation. What if I want to add animacy annotation to my AGDT, to my ancient Greek dependency Treebank files? How would I query that? How would I add? This is probably more for the maintainers. than it is for the general users. But if it's if you got the extensibility, this power of extensibility, so you can add new text and also new annotation layers, that's a plus. So this is one type of a synergy that I found very useful in my previous research. Treebanks, as you probably noticed, don't have the information of who is speaking. Gabby knows that this might be a very interesting research question. But digital editions, especially those in the Perseus digital library, were encoded using this format, TEI XML, which you probably know. They do have this information. So how can we make use of the fact that a Treebank text is based on a TEI text that has this information, even if and so this information is retrievable even if we don't have this information in the Treebank itself? And this is an important question. And so, just to summarize what I said, here are a couple of what are technically called user stories that I like about Treebank. So, simple real-life scenarios that I think would be extremely interesting for us to evaluate our system, a query system, work. And by all means, you can all come up with as many user stories like that as you want. But these are two of my user stories that really came out of on the top of my head for this session. For example, what can you do with a Treebank? I would like to be able to inspect all construction like the genitive absolutes, which you might know in Greek is pretty much the same as the ablative absolute of Latin, or all the construction accusative plus infinite in Homer. This is a real-life use case that people might have for your Treebank. Another one, I'd like to know what are the most frequent compounds of sun, preposition sun, pretty much like cum in Latin, used by each character in Sophocles. Can our Treebank query language support all the needs of these two people presenting these two use cases? Well, I think this is an interesting question. So let's briefly see in action the two projects that I mentioned before. The first one is structural search. And let's probably try to measure it with the help of this use case. So what is structural search? It's a web-based search engine for the Treebank, which has three great advantages and some disadvantages that we will see in a second. It's simple, very powerful, and very fast. It's very simple because it's practically based, so the query language itself is based on CSS tree selector syntax. So I don't know if you have ever played around with web designing, construct websites. If you have, you've probably had the experience of tweaking out the style of your web page and try to construct a beautifully looking web page. To do that, you will build a CSS file that you will write CSS and link to your web page. A CSS file that will say how to format each of the elements in your HTML, and you will select each of those HTML elements using CSS selectors. And this CSS selector is what this structural search implement to search for the elements within the Treebanks. But let me show that in action. Here we go. So this is the web page of structural search. Another great thing about it is that it has some real life example and a very, very easy and easy to read and very comprehensive query guide. So let's probably first start by having a look at that. So each of the morphological attributes, like the one that we saw before, like for example the case, the mode for verbs, the number, the person, etc., are accessible using this colon syntax as pseudo selector in CSS, if you know something about CSS. So you can very easily start a query like that. This query will get you the third singular verb, third person singular verb. That's right. Well, you can even click here and we would be probably brought to, okay, yeah. You see how fast it was. You see one, and you see how the results are returned. So is this fast? Yes. Is this simple? I think so. Is this comprehensive? Well, these are the texts that you can access. Not really hold the text in the AGDT, as we said. And since this site has not been updated for a while, there is no way to access the newest annotation. How is the output? Well, you have at least a count of the result, the sentence in continuous text, and you can click on that and have information. But it's not great because I don't see where the verb the result that matches this query is. But at least we can work with that, right? It gives us some information. The results are paginated, so you can continuously work. Probably for those of you who are a little more technical, you see that it's that the query syntax is implemented over here, so it's very easy to program something, to programmatically use this query language. So to write code, to write scripts, for example, that would perform queries on this system. Let's continue to have a look at the syntax. So it's programmed to work directly with lemmas. So if you chain pseudo selector and use a lemma, you can get all the things that you're interested in. How is syntax encoded? Similarly to how it is very similarly and how it is represented in Ines. So for example, here you just use this greater than sign and linked it to a lemma, and you encode the label at this level as an attribute to the governed element. So this query, for example, will give you optatives that govern the conjunction a, which is the same as if in English, roughly means if in English, with the syntactic label used for the auxiliary conjunctions, so the conjunctions governing a clause in the formalism of the AGDT, governing an optative. Let's see it in action. Again, very fast. And here are the results. So this is pretty much okay. Then it supports, as we said before, word order. Okay, so order of the words. So it's, as you see here, it supports the chaining of words following at some distance, and this kind of thing. So it's kind of powerful. You can already start doing, even if not the most powerful, the most important, the most developed slide that Doug had, unfortunately, to skip. It supports some powerful query on the text of Homer. What about the ones that we said before? What about the sum? What about, for example, the regular expressions? Well, there is no way, even if we just select one text like the Humanities, right? Play like Humanities, where we have characters, but we have characters also in the Iliad and Odyssey. It's impossible to limit the search to search for the certain forms of certain construction within characters. It's also impossible to search for regular expression because this is not supported by the CSS selector, unless it's a very limited regular expression, like the string, like the form of the string begins with. So you can use this caret sign to say it begins with. But for example, here, if we want to say we want the epsilon and the accented epsilon, we can't do something like that, right? We can't write the regular expression as we would by saying, okay, this and the accented epsilon. I will not do it. But let's run this search. Did I? Oh, yeah, of course. Forgot to take this. Okay, so again, fast, and it gave us some results, which I can't find, but yes, you can see that this is the matching one, and so on. This is the other matching character. So, well, it get, and then you can substitute it that by saying, okay, I want, right now, then I want the accented version, right? Okay. That's like this. You can do search for the other examples. So that's already something. Then I will very briefly talk about the advantages of using a more complicated system like this one. So what is the GAGDT? Well, the GAGDT is simply, as you can see from this link over here, a project that I started and I'm running on my own. It's a conversion of the data of the ancient Greek dependency tree bank, just the Greek, unfortunately. So you see that there is no other way than what Doug mentioned, using the universal dependency to work with the, unless you want to do, of course, something like that. So the GALDT, or so sorry, the GLDT for the Latin dependency tree bank. So the conversion of the Greek data of the ancient Greek and Latin dependency tree bank into the structure of a graph database, using one engine for one management system for graph database, which is very popular right now, Neo4j. And then those data are structured using the structure of a graph database, a graph structure, with where everything is represented as nodes, having properties and links to other type of nodes. Let me show some. Let me show you my web page for the graph in GitHub for the GAGDT. I have written some information about that. So what type of schema I use, what type of nodes are there, what type of relation I implement, which are very basically just the dependency relation. One big advantage of this is that it's flexible. It's fast and scalable. It's very flexible. I can extend that as much as I want. If I want to add animacy, that becomes yet another property in the nodes that I can add. If I want to add other type of relations between words, I can add them. But the great thing, the thing I like the most, is that it implements a very powerful yet simple, intuitive, let's say, query language that expired by another popular query language, SQL, for databases. And it's based on ASCII art, so the same type of things that you could typically use when you type emoticons on a keyboard, like, so that you drive the arrows like that. So that basically you will write and create a node and query property values like that, and use this type of syntax, yes, to query for dependency relations. So how hard it is to install? Not very much. You would just basically have to download the database that I provide. I provide a link and some instruction for that, and download the graph database management system, Neo4j, on your system. But it's, especially if you're on a Mac or on a Windows, it's like one click and on an install. It's nothing very difficult. But let me show you. Well, let me run the query that I showed before. Like, okay, so let me show how to start a query. So, for example, let's say we want a token that's going to be the head. So we were pretty much like Doug did. We are labeling this as a H. We want to create a relationship. Yeah, we can say that we want it to be a dependency relation, and I can add a type, right? And I can add the fact that I want this type to be SBJ, subject. And then I queried a dependent, and I want it to be a token. Then I want it to return H and D. Well, we limit this to a couple of 5 nodes, let's say. So here we are. Is it graphical? No, it's not. It supports the graphical. Okay, I am using here a console for issuing Cypher query. That it's provided, comes with Neo4j. Definitely, you can create websites that query the database and display the results, but that escapes my knowledge for doing this. Sorry for a second. Just allow me a second. But you can very, very easily have tabular results. So for sake of brevity, so that I will stop here, let me show you. I have already run I have already created for you the type of query that I was mentioning before, the one that will get you all the character count of the compounds of Sun in Sophocles. So I'm using a regular expression here, and as you can see, I have myself by matching the Treebank with the digital editions in Perseus, I have added some attributes to the sentence level. So, for example, the author, the fact that the author is Sophocles, and the speaker of a sentence. So let's see. Let's run this query and let's see what it gives us. It gives us a count. Well, it won't do very much with that, but it's already a starting point. It gives a per characters. Obviously, chorus is not very informative because it's all the choruses in all the tragedies, but yeah, we can start with that. Of the compounds of Sun in the tragedy of Sophocles, and then we can rerun this query by, for example, getting the for example, the list of lemmas and forms. Okay, so we say that the first one in the Ajax of Sophocles. Well, we can also get the, why not? Let's have also the title of the tragedy. So as work, and we give a beautiful name to the column, like say work. Okay, from the Ajax, you see you have Odysseus using this form from this lemma, and so on. This is very useful. Okay, this aliasing as work, as character is very useful if you then want to dump everything to a CSV file, which you can do very easily in the console from here, and so on. So that is a powerful solution, obviously. Is it easy for the average user to learn, use, and maintain? Probably not, but it's not that difficult. You can try yourself from here by following my instruction and getting back to me if you need some help. How to do that? It's basically pretty easy, and you have information in order to do that. And I have written a couple of exercises for you to complement what the exercises that Doug was proposing, which is basically pretty much what Doug was doing in his last slide, taking a study. In this case, it's sorry for the shameless self-advertisement. It's a study that I did myself, but it's where I have the most experience with working with querying Treebank data on a syntactic construction, right? So the agreement of subject and verbs in the case where you have coordinated subjects. You can try to replicate my queries by using Nick Calden's structural search, and if you are brave enough, using the graph HEDT if you want. So that pretty much concludes what I wanted to discuss with you here.
Thank you, Francesco. That's great. There's lots to look at there. And thanks also to Doug, although I think he's left us. As have a couple of other people who left comments on the Hangout saying thanks, but they had to leave early as well. Anisa has just asked a question in the comments. Let me see if I can find the comments so I can read it. So yeah, Anisa asks, what do you think about AGDT querying on Tundra? I suppose you can't add other annotation categories on that.
No, not as far as I am aware of. The last time that I checked, oh, sorry, am I muted? No, you can hear me, right?
Yeah, we can hear you. Yeah.
Okay, good. I'm sorry. Last time I checked, though, I wasn't able.
See you there.
Yeah. Last time I checked, I couldn't access the Tundra interface for the ancient Greek dependency treatment, to tell you the truth. So I was never too familiar with that, especially because, to tell you the truth, I'm not scared of getting my hands a little bit dirt with coding if I have to, but I really like having flexibility. So I really like to manipulate my stuff myself. So changing stuff, changing annotation if I'm not happy with what I see, and this kind of thing. So typically don't work with those web-based projects. I prefer to handle this the files myself. So this is why probably I'm not the right person to ask.
Okay, thanks. Does anyone else have any questions they wanted to ask or comments on this session? Doug isn't here to answer questions, but you can try asking questions about Ines as well, and we'll try and answer it between us. The question I have briefly, this is maybe a sort of big and philosophical question, but is what are the potential for bringing these various different interfaces together? If someone likes the Ines search interface, for example, could they import the AGLDT into Proel somehow? Or vice versa. What other because having multiple different tree banks, which each one has to have a different method to search, is obviously slightly less than optimal.
Yes, it's I'm not sure, because this depends very much on how they implemented. But one big problem is the fact that all those projects, though very similar, have some differences in the annotation schema that they use, which might be totally legitimate, because people it's very hard to find two linguists who would agree on what syntax is, let alone how to represent it, right? So even if we must make the most of the efforts to standardize everything, disagreements and differences will always be, I mean, disagreements on the meta language on how to describe stuff, not on on the description itself. Will always be there. So that's why also one project that Doug had to mention very briefly, unfortunately, which is universal dependency, is extremely important, because universal dependency, what universal dependency aims to do is exactly that: uniform all these annotation systems. And so once you have those annotations uniformed, then you can do exactly what Ines does. So have Afrikaans and ancient Greek on the same tool right away with no problems. So that's probably one question that I forgot to address on my presentation, but it's a totally legitimate question. Doug mentioned that the ancient Greek dependency tree bank is it was converted and it's distributed together with the other tree banks of universal dependency. Can't we use that instead of using all the system that I presented in this session? Yes. The problem with that is the fact that I'm not entirely sure, but last time that I checked, last conversion of the ancient Greek dependency tree bank, there were some problems, and so not everything was converted. And logically, if you do a study on Sophocles, for example, you really want to use everything that is there, or at least being 100% sure of what is there and what is not. You can run the risk of basing your own conclusions that you think will revolutionize research on Sophocles on data that you don't know if they are complete or not. So that is why I would say that universal dependency is great. It's a fantastic thing, but it's still not there, not quite there yet. We are not quite there yet. The conversion was not easy and not complete. But as soon as Giuseppe or the other people working will find a solution for how to convert smoothly then obviously this will become an option, using a universal dependency as an harmonized version of the tree bank together with the other tree banks, not just the Latin, but really everything.
If you know, is the issue with conversion just that it's complicated, that it's not simple one-to-one conversion, or is it that the conversion would be lossy in any case? That there are some things that you represent in AGT that you just can't represent in universal dependency, so it would be lost?
It's lossy. Yes, there are things that are lost. Basically, because universal dependency, as far as I know, the universal dependency tag set is very expressive, but unless you re-annotate what is missing, there is no way to get this information from the AGDT, and vice versa. So in the end, yes, there is some loss of information, and there are a few things. Like the usual suspects when you think about syntactic annotation, like ellipses, for example, that are treated very differently, and are not easy to harmonize at all.
Gotcha. Thank you. Did anyone else have any? I mean, we've been going for quite a long time, so. But does anyone else have any last questions or comments before we end? Okay, in which case, thank you again very much, Francesco.
Thank you for the invitation and for listening to me.
Great. And we'll see you all again next week for the first of two sessions, which will be the last two sessions in the spring semester. We'll have then a short break followed by the summer semester. And next week will be the first of the two sessions on Introduction to Python. And Francesco will be joining us again along with Simona Stoyanova, who we all know very well. And they'll be introducing Python and, again, rehearsing regular expressions and looking at some of the things you can do with that. So we'll see you all next week. Thanks a lot. Bye.